All right, for the final topic of this week and of our geology unit, here are the big ideas, okay? So you should be able to answer by the end of this. What is absolute dating? What does it mean to say that an isotope is radioactive? What are parent and daughter nuclides? What is a half-life? And how do we determine the age of a sample using radioactive dating? And page 8 of our data booklet, because that's really where we need to go. Okay, so we're on page 47 from the notes, and please also take out your data booklet. You are going to need this thing, the decay curve. It is on page 8, like I said. Or if you've misplaced your data booklet, okay, or you didn't grab it before we switched to offsite, there's always a digital copy in the agenda or in the Google Classroom, okay? But you're going to want your data booklet for this stuff. All right, so again, page 47 in the notes. We are starting now with absolute dating. So remember, the difference between absolute and relative dating was that for relative dating, we had to compare to something else. So we said older than blank, younger than blank. With absolute dating, we are actually going to give an age. We are going to say, this rock is blank years old. Not just that it's older than something, not just that it's younger than something. We're going to say how old it is, roughly. Okay? All right. So how does it work? Well, it relies on something called radioactive decay. Okay, so remember back from our chemistry unit, all elements have isotopes, which means the same number of protons but different numbers of neutrons. Because if you have a different number of protons, you're not that element anymore, right? So looking at the example here, they have carbon 12 and carbon 14. Notice they both have 6 protons, right? So the protons in this picture are the red ones. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Good, because if it didn't have 6 protons, it wouldn't be carbon. But there's no rule about how many neutrons you can have and still be carbon. So neutrons, we have 1, 2, 3, 4, 5, 6, right? For a total of 12 things, 6 protons and 6 neutrons. Over here, though, we have 1, 2, 3, 4, 5, 6, 7, 8 neutrons for a total of 8 plus 6, 14 things, right? 14 protons and neutrons. So that's why we call this one carbon 12 and carbon 14. They are 2 different isotopes of carbon. Now, they have the exact same chemical properties, so they'll behave the exact same in chemical reactions, but in physical reactions, like in nuclear reactions, they behave differently. Okay, now the thing about carbon 14 is that it doesn't really want to exist. Okay, it is what we call unstable. It would really like to decay. It would really like for one of its neutrons to become a proton. I know that sounds like magic. It's nuclear physics, okay? It is the process by which it happens. Essentially, a neutron becomes a proton. And when it does that, we say that it's radioactive, okay? It sends out radiation. It sends out energy. Actually, that's the idea behind nuclear energy is you let things decay and then grab the energy that comes out from that, okay? So carbon 14, what it's going to do is to have one of its neutrons become a proton. If it gets one more proton, how many will it have? 7, right? It'll now have 7 protons. Remember, it still has 14 things total because it didn't just gain a proton. One of its neutrons became a proton, right? So if it has 7 protons, if you look at your periodic table, you'll see that it is now nitrogen. Yes, it has literally become a different element. Carbon has become nitrogen, okay? So we call that process decay. Carbon 14 is radioactive and will decay into nitrogen 14. That's kind of just what they're showing here. Notice how we had carbon 14 and it decayed into nitrogen 14, which is stable. So this guy, unstable, doesn't want to exist. So what does it do? It decays into nitrogen 14, which is stable and is just fine with existing. So when an unstable nuclide becomes a stable nuclide, we call that process again radioactive decay. We also call this one is called the parent, okay, the parent nuclide. This one is called the daughter. So it kind of makes sense, right? Because the daughter came from the parent, right? So the parent created the daughter by going through radioactive decay. So again, the original one is called the parent nuclide, and the isotope that is formed is called the daughter nuclide. Now, what becomes important here is something called the half-life, okay? What is the half-life? Well, this is going to keep happening, right? There's billions of carbon 14s. They all are unstable. They all don't really want to exist. So over time, they are going to start to decay. Now, they don't all just do it right away, okay? yes, carbon-14 is unstable. It will decay, but there's billions of them. It takes a while. They don't all just do it at once. They kind of have to go on existing for a little while until then they decay. So what that means, what the half-life is the time required for one half of the parent to decay into the daughter, right? So when one half of the carbon that we started with, let's just make it simple. Let's say we started with 100 carbon-14 atoms. Well, when we have 50 carbon-14 atoms left, one half-life has gone by. Another half-life has gone by when half of that is gone. So if we go from 100 to 50, that's one half-life. If we then go from 50 to 25, that's another half-life, right? Then we have to go from 25 to 12.5, that's another half-life. It just keeps getting cut in half every time a half-life goes by. So every radioactive isotope that exists has its own half-life, and that is the time it takes for half of the original amount to decay. What does this all have to do with dating rocks and fossils? We know these half-lives really, really well. So we can look at rocks and fossils that contain these radioactive isotopes, and we can look at how much of the radioactive parent is left compared to the stable daughter, right? And since we know how long it takes for those things to decay, we can put together how old this thing must be. So here we have what's called a decay curve, okay? So every radioactive isotope decays following this graph. It makes sense because let's look at it here. So here we have on the y-axis the parent nuclide remaining, right? So this is the unstable thing, the thing that doesn't want to exist. When we start out, see on the x-axis, we have number of half-lives. So that's how many times it's been cut in half, okay? So when we start out at 0 half-lives, we obviously have 100% parent. All of that parent isotope exists. It has not started to decay yet. Now, notice after one half-life has gone by, how much do we have left? Aha, 50%. Well, 50% is one half, okay? Now, this becomes like our new original amount. So when another half-life goes by, we'll have half of that left. So let's see, when we get to 2 half-lives, sure enough, look where we're at, 25. And yep, 25 is half of 50, right? Let's go to 3 half-lives. So now we'll have half of 25 left, right? So what's half of 25? Well, it's 12.5. And yeah, that looks like about where we are, right? Then we'll do, after another half-life, half of 12.5 will be left. And so we go to 4 half-lives and 6.75 is half of 12, right? Looks about right. It gets smaller and smaller and smaller. Half of the material goes away every time. It decays, okay? And again, we know very, very precisely how long it takes for one half of the parent to be gone and become daughter, okay? So just kind of wrapping your head around what a half-life is here. At the beginning, there's 100% parent, right? After one half-life, you got 50% parent. Then after another half-life, half of that is going to be gone. So we'll have 25% parent. After 3 half-lives, we have to cut that in half, right? Divide that by 2. So like we said, 12.5. Now, this seems kind of crazy to make you do it 10 times. Unless you notice, what are we doing? We're taking, right, 100% to get to 50. We're going 100% times one half-life has passed. So we're left with 50%, right? Then we're going to take 100% times one half-life times another half-life to get 25%, right? So 100 times one half, that'd be 50, and then cut that in half to get 25. That's 2 half-lives. For 3 half-lives, right? For 3 half-lives, what did we do? We took 100, cut it in half to 50, and then another half-life went by, so we multiplied by a half again. That brought us to 25, and now we're saying another half-life is going by. So that's going to give us 12.5%, okay? You might notice, what are we doing here? We're taking 100 times 1 half to the power of number of half-lives, right? Because every time a half-life goes by, we're going to multiply by 1 half. So put it to the power of that, right? So to get after 10 half-lives, we would take 100% times 1 half to the power of 10. And you'll get that 0.1% of parent is left. Okay, quick question for you. If at the beginning there's 100% parent, how much daughter is there? Remember, parent becomes daughter. So if it's all parent, that's 0% daughter, right? Now, if there's 50% of the parent has become daughter, how much of it is daughter? Right, 50%. It's 50-50 at this point. 25% of it is parent, the rest has become daughter. Well, then you have 75% daughter, right? The rest is daughter based on what you started with. Okay, if 12.5, so we're just taking 100 and subtracting how much is parent because the rest will have become daughter, right? So 100 minus 12.5, that's 87.5%. And after 10, we said 0.1%, so 99.9% daughter, which makes sense, right? Because the parent isn't just disappearing, it's just becoming the daughter. So every time a parent isotope disappears, a daughter isotope appears, right? So you can kind of see it starts out at 100 parent, goes down, and at the same time, the daughter comes up. Where do they meet? Where are they the exact same? After one half-life, when 50% is parent, right? 2 half-lives, 25.75, 3 half-lives, 12.5, 87.5. All right, so this is also on page 8 of your data booklet, okay? This is gonna be really important. So this is also on page 8 of your data booklet. And this just says what is a half-life. So how long does it take for these radioactive isotopes, these parents that don't want to exist, to become these stable daughters? So carbon becomes nitrogen 14, right? Potassium 40 becomes argon 40. Rubidium becomes strontium, and so on and so on and so on. These are the half-life in something called an annum, which is just a fancy word for a year. So you can see it takes for half of the original carbon 14 to become nitrogen 14, it takes 5.73 times 10 to the power of 3 years. Remember, don't get scared of scientific notation. It's still just a number. So you'll notice these are all really big, right? Like that's 9 zeros, that's 10 zeros, 8 zeros, 9 zeros. This is only 3, so this is 5,730, right? We would only move the decimal 1, 2, 3 times, whereas here we would have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 times, okay? Okay, so before we jump into some practice with this, let's just think about the formula, okay? You should probably write this in your data booklet or somewhere where you can look at it, okay? It actually makes a lot of sense. So we're going to figure out how many half-lives have gone by, right? The number of half-lives, and then we're just gonna multiply it by how long a half-life is. And then we have the total age, right? So just for example, if the half-life is 1 year and we find out that 3 half-lives have gone by, well, then it's been 3 years, right? 3 times 1. That's all we're doing here, except the half-lives we're going to deal with, because we're using them to date the Earth, which is old, are going to be a lot longer than 1 year, obviously, okay? So let's do some practice here. A rock is found to have 60% of its original potassium 40 remaining. So first things first, you go to the table on page 8, okay, and you're going to find potassium 40. So this is the half-life we're going to be looking at, okay? Determine its age. So this is how long it takes for half of the potassium 40 to become argon 40. Okay, great. But what we have to figure out now is if 60% is left, how many half-lives have gone by? So we're going to go up to our graph, and this is what you're going to do, right? You literally draw on it, okay, and you say, okay, 60% is gone. So you go over till you hit the graph, hit the curve, and then you see how many half-lives that is. So you just go straight down. And where you hit is going to be how many half-lives have passed. So to me, this would be 0.5, right? That would be 1. It's about halfway. So how many half-lives have gone by? About 0.75, okay? The total age is equal to the number of half-lives times how long a half-life is. So the approximate half-life is this, 1.26 times 10 to the power of 9 years. And if 0.75 of them have gone by, well, now we can actually figure out how old this rock is with an absolute number. We can say the age. We don't just have to say it's older than blah, blah, but younger than blah, blah. We can say it's blank years old, okay? So age equals number, okay? Like we just found on our graph, number of half-lives was 0.75, right? That's how many half-lives have gone by if 60% is left. And how long is one half-life? It's this many years. So 1.26 times 10 to the power of 9 years. I'm going to make a video just reminding you of how to enter scientific notation on your calculator, okay? But again, don't be scared of that. That's just a big number. If you want, you could just put it in your calculator first, get your answer, and then come back, okay? So I got, when I punched that in my calculator, I got that it was 945 million years old, okay? Or if you want, you can write that in scientific notation. Little review of scientific notation. The decimal's here right now, right? It has to go after the first number that's not a 0, so it needs to go 1, 2, 3, 4, 5, 6, 7, 8 times. Both are fine. I'm not as worried about sig digs as I would have been in our physics unit. Let's do the next one. A sample of wood found in a cave has 25% of its original carbon-14. How old is it? So try this on your own if you're feeling good with it. Okay, pause the video and then you can come back and see my answer. But we'll try it out. So 25%. Hey, I know how many half-lives that is. Can you think of how many half-lives it is? 25 is, right? It's half of a half, right? So it's 2 half-lives, but we can use our graph here. So 25% of its original carbon-14. So we're going to be using carbon-14. This is going to be the half-life we're looking at. Now we have to figure out how many half-lives have gone by. So 25 is right in the middle of 20 and 30, right? Draw a line over till you hit your graph. And then once you do, go straight down to figure out how many half-lives that means. So like we predicted, right? 25%, which is a quarter, right? 25 cents is a quarter. Quarter just means half of a half. So 2 half-lives, right? We did 1 half and then a half of that. So 2 half-lives have gone by total, right? Just like our graph said. Okay, just HL short for half-life. So we said from our graph, 2 half-lives, right? Times how long is a half-life? Well, for carbon-14, it's this long. It's that many years. 5.73 times 10 to the power of 3. So 5.73 times 10 to the power of 3 years. Okay, again, annum is just a fancy name for years. I got 11,460 years old. So see what I mean? Absolute dating. We're not saying it's older than this layer or even that it's older than a million years. We are saying it's 11,460 years old, give or take. We're not saying it's perfect, but we're actually coming up with an age, right? This is saying you are 17. It's not saying you're younger than me, but older than a baby, like we were with relative dating, okay? All right, let's look at this one. Igneous rock has 72% of its potassium 40. Okay, so what do you think we're looking at? You guessed it, we're going to be using potassium 40 here as our parent. Okay, so we got to find potassium 40 again. Oh, we already used, okay, so we're using it again. Potassium 40, that half-life. And it said it has 72%. So we'll go to 70. There's a little bit of estimation, obviously, right? But 72 would be not halfway, below halfway, right? Probably right about there. So draw a line over till you hit the curve, right? The graph part, and then go straight down. And that looks to me to be pretty bang on as 0.5 half-life. So half of a half-life. So again, this is how long a half-life is. 1/2 of a half-life has gone by. So half of that amount of time has gone by, right? Makes sense. And so we said 1/2 of a half-life went by, and a half-life is this long. Again, don't be scared of that number. Just put it in your calculator and get it as a general number if you want. You don't have to deal with it in scientific notation, but your calculator can do that. You have a times button. You can put 10 and you can put to the power of 9, right? When I do it, I get 630 million years, or if you want to write that to scientific notation, decimals here, it's got to go here. So 1, 2, 3, 6, 7, 8. Just saves you some time. So that's how old it is. Okay, absolute dating. We're actually getting a number, and it's all just based on the fact that these radioactive isotopes are decaying, and we know how long that takes. So by looking at how much of them are left in a sample, we can say how old that sample is. All right, so I'll pull up the big ideas. Okay, what is absolute dating? Just in general, what does that mean compared to relative dating? What does it mean to say that an isotope is radioactive? What are parent and daughter nuclides? What is a half-life? How do we determine the age of a sample using radioactive dating? And page 8 of the book, data booklet. So for that one, maybe just kind of list the steps as if you were explaining it to a Science 10 student to just kind of get the process down, because it's always the same, right? Get the number of half-lives using the chart, multiply by the half-life for that using the numbers on page 8. Okay, so that wraps up topic 4 this week and our geology unit altogether. So next week we will be starting biology. Okay, so for practice with this specific stuff, try the topic 4 section of the practice assignment for the week. And if you're feeling good about all that, you've asked me all the questions you want and everything, okay, you're feeling good, you can go ahead and do the summative check-in for this week. Have a great weekend.